comparison test. Test this series, picking known series that looks a lot like it. The first part of this says that if all of the terms in the testing series are smaller than the terms in the known series, and the known series converges, then our conclusion is that the tested series converges. On the other hand, if the AKs are larger than the BKs and that known series diverges, and so does this series. Smaller than convergent is convergent, bigger than divergent is divergent. These comparison tests are good when you have numerators and denominators that just look like my counting variable, whether it's a k or an n, is raised to some power, whether it's whole number powers or fractional powers, but power expressions over power expressions. It's real easy to make a comparison series just by keeping the biggest power in each. Sometimes it's not so easy to compare size. So we can go to our old standby, the limit comparison test. We start the same way. We test AK by picking some BK. And then we look at the limit of the AK divided by the BK. If this limit is some fixed number L, L is positive and finite, then both series do the same thing. The zero case was that the AKs will converge if the limit is 0 and the BKs are known to converge. Because that mimics the fact that smaller than convergent is convergent. And the only way for the limit to be 0 is if the bottom is bigger than the top. If the limit is infinite and the BKs diverge, and the AKs diverge, that mimics bigger than divergent. It's divergent. Did you try any of the web work problems on 8.4 yet? And I guess it's up to me to come up with examples. What are you guys good for? test this series here. Let's go from k is equal to 2 to infinity, 1 over the square root of k plus the natural log of k. So what I'm going to do to this thing is just kind of estimate each of them or something like that. I don't want to do so much tossing stuff away. I'm going to pick my lookalike series. See if you agree with this. Well, the numerator is still going to be 1. Of the two terms in the bottom, which of them grows faster? The square root of k or the natural log of k? The square root of k does. In fact, I'm going to keep this square root of k here. And I'm going to say that the natural log of k is smaller than the square root of k. So I'm going to replace it with the square root of k there. So I'm calling my BK series 1 over 2 times the square root of k. Because I think it's easier to compare in a direct comparison now. But before I do that, can you tell me, is this series that I picked as my lookalike series a convergent or divergent series?
Convergent.
Okay, let's try the other choice.
Divergent.
It's a P series, right? P is a half. P is a half. It's going to diverge. Just think about what this looks like if you integrate it. If you integrate k to the negative 1/2, by adding 1, you get a square root of k in the numerator. And so when you take the limit to complete that integral, it's going to keep growing. It's going to be infinite. So it's a divergent P series. So I got a divergent BK. Now, in order to use the direct comparison test, my given series has to be bigger than my comparison series. And that's why I chose this way. Let's take a look at this. If I look at the denominator over here, that denominator is smaller than the denominator in my comparison series. Because I kept this the same, and I made this smaller than the next thing up in the Tower of Power. So my new denominator is going to be bigger than my old denominator. Well, I'm not worried about the denominators. I want to know the size of the entire fraction. So now I'm going to flip both of these. And that flips the inequality. So here's my AK term is bigger than my BK term. So my series I'm testing is bigger than the divergent series. By the direct comparison test, bigger than divergent is divergent. Our series diverges. So sometimes the direct comparison test is easy to do. So we got another one. Let's try this one. It's another sum from k is equal to 1 to infinity. Let's put 4k squared plus k divided by cube root k to the 7th. Let's make that more. Let's make that k to the 9 or 9. How about k to the 10th plus k to the 7th. Have that one. Now this time, since I have several terms in the numerator that are powers on k, and several terms in the denominator that are powers on k, I'm not going to do the direct comparison test. Because when I make my comparison series, I'm just going to keep the highest power of k in each, in the top and the bottom, and that's going to be my bk. And I'm not going to be able to tell if it's bigger or smaller, because I'm taking something away from the top, and I'm also taking something away from the bottom. So if I don't care about how they compare in size, then I'll do a limit comparison test. Okay, so I'm going to form the bk term by using the highest powers on the k. So I'm going to keep the 4k squared on the top, and I'm going to keep the k to the 10/3 on the bottom. So that'll be my bk series. The biggest powers are the ones that control behavior in the long run. So I'm going to pick my bk series. I have a 4k squared on top. And let me write that as a k to the 10/3 on the bottom. You simplify it and tell me if the resulting series is a convergent series or not. What does that simplify to? Well, I don't care about the limit. I want to know what that simplifies to. Right, limit to 0 again tells us nothing. 4 over k to the 4/3, which is another p series. Does this p series converge or diverge? Converges because p is 4/3 and it's bigger than 1. This is a convergent p series. But let's do the limit comparison test. Take the given series divided by our series and see what that limit is. If that's a positive finite limit, they both do the same thing. We're going to do this now. I'm going to take the limit as k goes to infinity of the AKs over the BKs. Given series over the series that I just built. So my AKs are 4k squared plus k divided by the cube root of k to the 10th plus k to the 7. Sad looking k on the bottom. I'm dividing that by 4 over k to the 4/3. AK over BK. So we do the algebra. We take this 4 over k to the 4/3, flip it over and put it up here. Oops. When I multiply that out, I'm looking at the limit as k goes to infinity. What is that? 4/3 plus 6/3. That gives me a 4k to the 10/3 plus k to the 7/3 Can you tell the value of that limit by looking at the ratios in terms of the highest power numerator and denominator? It'll be 4, right? The limit's going to be 4. Because this is a k to the 10/3, so is that. This is lower, that's lower. We don't care about those. Right? So 4. Okay, so then it's 4 over 4. Doesn't matter. That's still piece of finite, right? So it's still 4 over 4. The limit's going to be 1. But if the limit is any positive finite number, they both do the same thing. So we go over here and look at what our comparison series did. It converged. So our given series is going to converge. So both series do the same. Therefore, our given series converges. Right? So now I'm going to give you an example where the comparison tests aren't so handy. Either one of them. But if there are several terms on the top and several terms on the bottom, more often than not, several terms meaning added or subtracted from each other. Bunch of stuff added or subtracted on top, bunch of stuff added or subtracted on bottom. It's easy to do a comparison test. But here's an example where a comparison test isn't easy. I don't have a bunch of terms. I don't have anything I can throw away. All I have at my disposal for something like that is the test for divergence. So I quickly look at that and see if the limit goes to 0 or not. What does it do? Right, as k goes to infinity, which grows faster, square to k or 2 to the k?
2 to the k.
So that means the limit's 0 and I know nothing. When I make my comparison series, I try to throw things away. Well, there's nothing to throw away from the numerator. There's nothing to throw away from the denominator. So I have nothing to compare it with. Maybe at best I can compare it with the geometric series 1 over 2 to the k. So if I try that, let's do it. Try comparing it to the geometric series 1 over 2 to the k. So we'll try a comparison test. It's not going to work, so don't get your hopes up. There is no Santa Claus. Since 2 to the k grows faster than square root of k, that's my comparison series. It's a geometric series. What's my multiplier? 1 over 2. Is this geometric series going to converge or diverge? It will converge because it's smaller than 1. But if I try now the direct comparison test, I can't claim that my AKs are smaller than my BKs, because they're not. My AKs are bigger than my BKs because they have a bigger numerator. Bigger than convergent tells me nothing. So I can't use a direct comparison test. This goes the wrong way. I need it smaller than convergent to be convergent. What about the limit comparison test? What happens if I take my AKs over my BKs? What's that limit going to do? Say it louder. It's going to have the limit of the square root of k, right? As k goes to infinity, because the two of the k's will cancel. Well, that's infinite. Well, that's the wrong case too. In the infinity case of the limit comparison test, we need our comparison series to diverge. So that doesn't fit the limit comparison test. So neither comparison test works with something like that, where there aren't terms for me to throw away. I don't know how to integrate that. Maybe I could fake it. You wouldn't know because you don't know how to integrate it. You just believe what I'm doing. So we need another test. So we move on to section 8.5, and we're going to get 2 more tests. And they're both going to be your favorite tests. You thought you loved the limit comparison test because it did so much for you. These other 2 tests, you're going to like even more. You're going to try to do everything with these 2 tests. Well, everything doesn't work with those 2 tests either. But things that have powers of k work well. And I'm going to introduce you to series that have lots of factorials. If you see factorials and powers of k and products, then we're going to try the test in section 8.5, the ratio test or the root test. These 2 tests are so good, there's even a generalized version of them that'll help us out when our series has non-positive terms in it. But right now, we're still considering positive term series only. Okay, in the ratio test, we're going to look at a limit again. These terms march down in our sum where the subscript on the terms grow. So I'm going to take a bigger term over its next door neighbor and take the limit. So I'm going to take the bigger term, AK plus 1, and divide it by its neighbor, bigger being bigger subscript. I'm going to take the term on the right, divide it by the term on the left when I'm way out here in the sum. And I'll get some sort of limit. If that limit is smaller than 1, I get a conclusion. If that limit is bigger than 1, I get a conclusion. And if that limit is equal to 1, we don't get a conclusion. If the limit is equal to 1, this test fails. Because what happens if the limit is equal to 1? That means the next term is growing at about the same rate as the previous term. And so I don't know if my sum is getting small quick enough. I need my terms to go to 0, but I also need my sum to get small quick enough. So what's the better case? If the ratio of the next term over the previous term is smaller than 1, or if it's bigger than 1? Which one makes more sense in making the overall sum at the end start to be getting a bunch of zeros added there? We want it smaller than 1. If that ratio is smaller than 1, this term is going to be smaller than that one. And the series is going to converge. If it's bigger than 1, that means if this is bigger than 1, then that means AK plus 1 is bigger than AK. So my terms aren't getting small enough way out on the end when I'm adding them. So the series diverges. The reason this works well when I have powers of K and when I have products in the numerator and the denominator is that I get lots of cancellation. So it's easy to see limits. When I have sums and differences, I don't get cancellation. So a comparison test works better because I can just start throwing those terms away, right? So let's go to that series that I talked about, the square root of K divided by 2 to the K. Intuitively, I hope you think it's going to converge because it looked a lot like a convergent geometric series. It just had a square root of the K in the numerator. So let's see if that's going to agree with this. Let's use the ratio test. That's my AK term. And what I need to do is make this, look at what this term looks like. Well, that's easy. I just replace each K by K plus 1. So my AK plus 1 term will look like the square root of K plus 1 divided by 2 to the K plus 1. Here's my plan. I'm going to compute that limit. So now I'm going to do it. The K plus first term has each K replaced by K plus 1. There's AK plus 1. There's AK. Let's simplify that and see if we can take the limit. I'm going to simplify this by doing the flip and multiply step. And then I'm going to use the fact that I can write 2 to the K plus 1 as 2 to the K times 2 to the 1. Because when you multiply like bases, you add the exponents. So if you have something with added exponents, it came from multiplying like bases. There's not a thing I could do with the square root of K plus 1. But again, I'm writing 2 to the K plus 1 is 2 to the K times 2 to the 1. Then I'm going to take this division flip it over and multiply. Only one term cancels, but it's a pretty big term. I canceled the 2 to the k. And let's see what's left. That's what's left. Agree? Still want to catch up with you guys. Okay. So the AK plus first term divided by the AK term, flip and multiply, a little bit of simplifying, and I can cancel the 2 to the k term. Then you could look at your tower of power and decide on that limit. What is it? 1/2. 1 times the square root of k up here, 2 times the square root of k down here. The limit is 1/2. The size of the limit puts me in this category. My limit's smaller than 1. Boom, this series converges. So it did. It looked like a geometric series, but with an extra junk on it. Okay. Ratio test is a good time had by all. All right, now let's look at. All right, so okay, you got to remember this: smaller than 1 converges, bigger than 1 diverges, equal to 1. Try something else. Usually a comparison test. So the next one we're going to test two to the k divided by k factorial. I'm going to remind you what k factorial means. What is 4 factorial? 4 times 3 times 2 times 1. So we're going to write k factorial as k times k minus 1 times k minus 2, blah, 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 until I get to times 1. You're going to have to try to remember that when you have k powers and or factorials, no addition or subtraction, then the ratio test is going to work like a charm because lots of stuff will cancel. What grows faster, 2 to the k or k factorial? Where are these in our tower of power? K factorial is a faster grower, which means this limit goes to 0. So that means we know nothing, but we can proceed with a test. So we try the ratio test. The statement of the ratio test is that we're going to compute the limit as k goes to infinity. We make the ak plus 1 term and we divide it by the ak. Term on the right divided by term on the left. Where we form ak plus 1 by replacing each k with k plus 1. So in our example, our ak plus 1 numerator will look like 2k plus 1 divided by k plus 1 all factorial. And on the bottom, we have the series as we see it, 2 to the k over k factorial. So now I flip and multiply, and as I flip and multiply, I'm going to write 2 to the k plus 1 as 2 to the k times 2 to the 1. Flip and multiply, puts a k factorial up here, and a 2 to the k there. But before I cancel, I can cancel the 2 to the k's. Here's k factorial. What does k plus 1 factorial look like?
Equals one.
So it's k plus 1 times k minus 1 times k minus 2. In other words, it's k factorial times the factor of k plus 1. Agree? So let me write that here. That k plus 1 factorial is k plus 1 times k factorial. And then you can see the cancellation. Now let's cancel what we can. I can cancel a k factorial and a 2 to the k. So all I'm left with is 2 to the first power on top and k plus 1 on the bottom. What's that limit? The limit is 0. We're comparing it in size to 1. 1 is our conclusive number. If it's smaller than 1, it converges. If it's bigger than 1, it diverges. This is smaller than 1. Our series converges by the ratio test. All right, just to get us practicing on some canceling, let's try one very similar. Marked on my glasses. Which of you marked on my glasses? Let me see. Use the ratio test on the series. Let's go with k times 3 to the k divided by 2 times k plus 1 factorial. Again, in my training, you to recognize which test to use at which time, having powers of k and or factorials and no sums makes this a prime candidate for the ratio test. Right? Products are what get things to cancel. Powers of k represent products, factorials represent products. Okay, so let me give you a minute to set up this ratio. Carefully. Replace each k by k plus 1 and put that in the numerator, then put that expression in the denominator. I want to see if you're going to set it up correctly, and then if you know how to cancel it correctly. I'm gonna catch up with you before you do too much damage. Okay, so I'm gonna tell myself I'm using the ratio test. And then I'm gonna tell you what the ratio test looks like. And then I'm gonna do it. So I'm gonna make this into a K plus one, and make that into a K plus one, and I gotta put a K plus one right here. So I'm gonna have K plus one, 3 raised to the K plus one, 2 times K plus 1, now put the parentheses and the factorial back on it. And if it doesn't bug you too much, I'm going to do the flip and multiply step right now. Is that okay with you? If it does bug you that much, then you've got some issues that you need to work out with somebody more professional than you. Okay, we know we can describe 3 to the K plus 1 as 3 to the K times 3 to the 1. Let's work on the factorial term. If I were to distribute this 2 and then add the 1, I get 2K plus 3 factorial. So I'm thinking somehow there's a 2K plus 1 factorial lodged inside of the 2K plus 3 factorial. How far down the line would it be? 2K plus 3 factorial has a 2K plus 3 times a 2K plus 2 times the 2K plus 1 factorial. So let me make that note right here. Run it sideways so those folks on the screen can see the whole thing. And they almost could. So that means I can cancel the 2K plus 1 factorial, and it leaves me the product of 2K plus 3 with 2K plus 2. So these two terms are going to be left after I cancel the 2K plus 1 factorial. And that leaves me 2K plus 3 times 2K plus 2. No factorials anymore, just a dry old product. And then the 3 to the K's cancel. So without the red on it, on top I have K plus 1 times 3. In front. On the bottom, I have 2K plus 3, 2K plus 2, and this little K down here. So on top, I have a first degree power of K. On the bottom, I have a third degree power of K. What's the value of this limit? 0. Very bottom heavy. This limit is 0. Our comparison number is to 1. The limit comparison test smaller than 1 means we have a convergent series. I kind of want to show you what will happen if you try to use this ratio test on something without factorials or K powers. But instead of wasting my 1 whole minute doing that, I'm going to show you what the kth root test is. The kth root test is what the ratio test is, except you grab the kth term and you take the kth power of it. If that has a limit that's smaller than 1, it converges. If it has a limit that's bigger than 1, it diverges. If its limit is equal to 1, we don't know. Compute the limit. As k goes to infinity of the kth root of the ak terms. Then we get some number L. And with the same 3 conclusions, if L is smaller than 0, the series converges. If L is bigger than 0, the series diverges. If L is, oops, I'm not 0, 1, take the 0 away. If L is smaller than 1, it converges. Bigger than 1, it diverges. If L is equal to 1, I don't know. Test is inconclusive. So don't use this unless you have a series in which everything in the series has a power of k. If every piece of it has a power of k, do the kth root test. If there's some of it without the power of k, not such a good idea. Okay? So I'll do an example of that next time. I'll do an example of where the ratio test doesn't work for us, where maybe a comparison or integral test would be better.
We can use the ratio test on all of the series that we've done so far, right?
If sums are bad, and that's what I want to show you next time. If I stick a plus sign, if this were k plus 3 to the k, I'd rather use a comparison test because nothing cancels through plus signs. So if you did homework on paper and turned it into me, I've got some of them graded. We're also going to start looking at series that have terms that are negative. So on Blackboard, I'm going to put a list of all of the positive term series that we have now. Go ahead and run that off so that you can look at it and decide which test to use when. Okay, so over here I have my stuff there. You can trade me? I got Jeremy and Elizabeth. Jeremy's gonna trade. Everybody good at home? Questions, anybody?
I can try, but there's a good chance I won't be able to.
Well, I mean, you didn't write your partial sums in closed form. You're gonna make it a sequence first. It's not that easy to just eyeball it and say everything's gonna go away, just leave you 1/3. Give me the general term, so in general, my 2 last terms over here will be 1 over 2k, 2n plus 1 minus 1 over 2n plus 3. But our pattern shows us the one inside is going to cancel, so you'll be left with the first and the nth for Sn. Sn is a finite sum. You stop it at n.
Right. So that happened.
So you write it as a finite sum as Sn, and then if the Sn's have a limit, and that's the limit of the series.
Oh,
So
okay,
it's
so
a
you gotta go
little
ahead
formal
and,
step in there.
so you gotta say the SM, this one right here will be equal to 1/3.
But if I
Yeah, that
replace
one
the
there,
K's with N to get the
Right.
dot, dot,
then
dot,
you say
stop it
that
at
one
the
right
end.
there equals 1/3,
Mhm.
then you can write it out that way. Oh,
And
okay.
then we stop it at the end. And we saw that the inside one was going to cancel. on the pattern.
Oh, okay.
Okay.
That makes a bunch of sense, thank you.
Do you have a quick math question?
I was just gonna tell you I'm not gonna be here on Friday.
Taking a long Easter weekend, huh?
Yeah, my brother has a track meet, so.
Cool. What's he run?
He wrote these triple jumps and long jumps.
So
and
he's first, so you gotta get there first.
I know it's at like 9 o'clock in the morning.
I was gonna say if it's mile relay, you got time for class and then you go to track meet.
Yeah, no, and he also runs the quarter too, so that's pretty late.
Wow, busy dude. All right, well, have fun. I'll
Alright.
put this online and you can, lately it's giving me about a day lag for me to download it.
For
Um,
the,
for
oh,
the-
put it on, oh,
so it-
I'll try to make it to the
You'll try to make it to the live class?
lecture.
Okay.
just Online.
Okay, but it has been taking me a long time to get the tape going back before I can post it.
Okay. So many people skip for like, say they weren't gonna be here Friday, my first class today, that you just canceled it for
But I'm not
Friday.
gonna do it.
That's
I'm gonna
fine.
do it. But you're not
So-
gonna be here Friday?
No, I will be. I'm taking either honors physics 2 or honors calculus 3 next year, and I have no idea.
You can't do which one?
I can't
They're
do
at the same
both.
time?
Yeah, it conflicts also. I don't want to take both. I
Okay,
didn't know if you had a recommendation for,
who's our honors Cal 3 professor?
Oh, I got you on that one. There, you've got, one guy that's called, you have one guy that does Monday, Wednesday, Friday at 12 to 12:50 right there. He's pretty good. He's got a 5.0 on Rick Professor.
That's pretty good.
Yeah, he seems like a.
That
pretty
must be
good person right
Eugenio
there.
Elisa?
Nope, he's got a 4.0 on Rick Professor and he is on Tuesdays and Thursdays. I'm
Okay.
taking him next semester.
I think there's only one potential Cal 3 honors next semester.
No, there's two.
Is there 2 of
There
them?
are honors right there. One honors is Monday, Wednesday, Friday, 12 to 1. Here, let me pull it up for you.
And I think you'll want to Cal 3 on Tuesday, Thursday, because the problems are long.
Like
Tuesday, Thursday's better, because then the
Right
professor
now-
can actually finish an example.
Okay. I took that out of necessity. I'm glad that works. Or I'm going
I'm
to
just
take
gonna
that
be
out of necessity.
selfish and say we have better Cal 3 professors in general than there are physics professors. So if you can do physics honors, I think that's a good deal because you get the better of the physics professors. Or any of our Cal 3 professors
They're gonna be just
are gonna be
fine.
pretty good. They'll be graduate students, but they've been doing Cal 3 for a while and they're handpicked to do Cal 3 because they're better than the other grad students.
And I feel like math is just simpler than physics too.
And if you
In-
get stuck
in a
on
good
math,
way.
you can send me an email, say, hey, how do I do this? And I can help. But if you ask me physics, I can just say,
This is the person that does it right here. That's one of them. And then this is the other one that is on Tuesdays and Thursdays. And this is on the.
So it is, and we don't have to get any permits or anything to take that, right? Okay, awesome. Well,
Apparently not, because nobody except for select few majors needs Cal 3 or the biochem and biology Cal 2. But I need Cal 3.
I think I need Cal 3. I'm sure computer science.
yeah, because
I think it's on the list.
you're gonna need linear algebra and,
Yeah, that's my next one on that, so I'm pretty sure. Awesome.
yeah,
Well, thank you.
but linear algebra only has a Cal 2 prereq. So if the honors linear algebra fits your schedule better than Cal 3, you can do that sequence.
Okay. So I don't need to do Cal 3 before linear algebra,
You know,
and it would matter if I did those. That's something to look at. And registration is Friday, so I just need to get it figured out by then. Yep.
So I gotta warn you, we got some crappy teachers for linear algebra. So if
Okay.
you do the honors linear algebra, I think you're
Definitely.
okay.
Unfortunately, now that I think about it, that one was, I think, when you had to get a PRF filled out for,
Right.
which I didn't do. So,
Well, I do the calculus.
So, but do physics 2
honors this semester?
Yeah,
Pretty good?
it's going all right. I don't know. Physics is fine until they start trying to add calculus into it. Because the way that they try and integrate calculus is not how I learned calculus in these classes. It's like,
Well, wait till you get to your engineering that doesn't do the physics and the calculus the way you learn to do the physics and calculus.
I won't have to do too much of that because computer science is definitely more.
True.
But if I do, I'm gonna have a lot of open elective stuff that I might want to do engineering with the next choice.
Yeah, so for computer science, the physics 1 and 2 is just read out courses.
Yeah,
They're not really,
Pretty-
whether you know the physics for computer science. Let's just get rid of the bad computer science majors. That's just to give us math majors.
that's what they talked about in engineering. They're like, probably about 50% of you are gonna turn into math majors within like the first 2
We
years.
have 385 math majors, and you can't tell me 385 students in college saying,
I'm gonna be a math major. All right, well, thank you very much.
you're welcome very much.
Appreciate that. You have a nice, well, I guess, weekend.
Yeah, we got a Friday to do. Don't you ditch me now.
Doesn't feel like a Wednesday.
It doesn't, does it?